Okay, so 11.2 is all about rational exponents. Rational in a math class means fractions. And so I kind of hinted a little bit in 11.1 when we were talking about radicals that there was a way to represent your radical with a fractional exponent. And that actually helps us to compute or to play around with these different exponents. And so that's what we're going to do today. We're going to do a lot of, I'm just going to move it back a little bit. A lot of going back and forth between radical format and our exponent format. Because sometimes it's easier to simplify a problem when it's a radical. Sometimes it's easier to simplify a problem when it's fractional. And so based on Pearson, make sure you read the instructions and what it tells you. If it wants it with rational exponents, give it to them in rational exponents. If it wants it in radical form, give it to them in radical form. And if they want it in radical form, sometimes they will even specify not to simplify it. And they literally just want you to put it in radical format and not do any simplifying at all. And so just be careful that you read all the little blue words next to the answer box so that you can answer in the appropriate format. So here's how it works. This is going to be the process that we're going to use going one direction to the other. If we are given the radical format, we have our index on the outside and we have whatever's inside our radical in here. And so when we convert it over to a fraction, little exponent, what was attached underneath your radical goes on top, and that index sweeps around and becomes the the denominator of your fraction. And so the way that I kind of like to remember it is whatever's on top of your fraction stays with the base of your exponent, and the denominator sweeps around to be the index. And that's like the only thing I can kind of do is the top number stays under the radical or stays as the top number of your fractional exponent. The bottom number is the one that ends up moving around. It's the one that pops outside your radical, or it's the one that pops down below to your denominator. There's a couple of interesting things to note. That if your A is greater than or equal to 0, so if it's 0 or a positive number, whatever you're taking the radical of, then your n can be any index. And we actually saw this in 11.1 because we talked about whether or not we would get an answer or we'd get a not real situation. So if A is positive or 0, your index can be either a negative, or excuse me, either an even or an odd index. But if A is less than 0, so if A is negative, then your index has to be odd in order to get out a real solution. Because remember, we can't take the square root of a negative number. We can't take the fourth root of a negative number. And so that's all that those little notes are stating. And so look out for those because they will pop up in your homework. And you're always given the option to type in an answer or to indicate that your solution is not a real answer. And so you're always given those in Pearson. All right, let's do a couple of examples so we can see how this plays out and hopefully see how it's going to work. It says write with fractional exponents. So we're going to translate from radical into fractional exponent. So we first start with just the basic square root. Remember, if there's no index written out here, it's like there's an understood 2. But if we look at this number underneath our radical, there's not an exponent on it. So what exponent do we understand to be there? A 1. That's right. So if there's not an exponent given, we understand that it's just a 1. We just don't write it because we like to keep it as simple as possible. So when I'm converting from this format into my fractional exponent format, the 1 stays on top, the 1 with the 5, and the 2 is going to sweep around and become my denominator. So the square root of 5 is the same thing as saying 5 to the 1/2 exponent. And that's all I do. There's nothing else for me to do. I wrote it in the fractional exponent. I'm done. In Pearson, what happens is you're given a bar at the bottom of your screen, and the exponent is an option, and then when you're in the exponent, you have one of 2 options. You can either then click on the fractional button that's given to you at the bottom, or you can use the slash on your actual keypad and type 1/2, and it will put it as a fraction for you. Either way will give you that fractional exponent. So if the square root of 5 becomes 5 to the 1/2, what is the cube root of 7 going to look like with fractional exponents? You what? Yeah, it's going to be 7 to the 1/3. Same concept. This has a power of 1, and the index of our radical sweeps around to become the denominator of our fraction. Perfect. Now, in my notes, I noticed that for the next two, I feel like I didn't take them out as far as I would like to. Having done the homework, though, I'm trying to see if there's a similar problem to the next two in the homework. Yeah, kind of. So just note that C and D in my handwritten notes, I only take it out one step, and I'm going to take it out 2 steps here to show you exactly how I would put it in Pearson and how I think they would want you to put it in Pearson. So notice that we have the 4th root of 11xy to the 3rd. This 4th root applies to everything that's underneath this radical. And so it would be 11xy to the 3rd raised to the 4th root. And in my handwritten notes, that's as far as I took it. I don't think that's as far as you probably should take it, because that exponent on the outside, the 1/4, applies to each of the terms inside. And so you need to distribute that to every single term that's in here. And you're going to have to remember some of your exponent rules from chapter 5, like 5.1 and 5.2, which I do list for you here in a couple minutes so that we can have a refresher. But that would be 11 to the 1/4, x to the 1/4, and then a power raised to the power. That's our power rule. And does anybody remember what we do when we have a power raised to the power? We multiply those. So it would be y to the 3/4. So distribute that power into each term that's underneath. You can try leaving it with just the parenthesis around it and seeing if Pearson will accept it. I bet you they're going to say that you need to take it one more step. But maybe not. I took it one more step when I did the homework this morning, and I wrote it out this way whenever I encountered a problem like that. And that's the way Pearson accepted it this morning. So, questions on that one before we do D? Questions on any of them, really? D, we have the 5th root of 7x over 11y. So again, the very first way we can write this is 7x over 11y raised to the 1/5. And that's as far as I took it in my handwritten notes. But again, I would recommend distributing that 1/5 to every term inside, so that you have 7 to the 1/5, x to the 1/5. None of these have exponents, so it's all just to the 1/5. Again, you're more than welcome to try this and see what Pearson says. Maybe they'll accept it, especially in these first couple of problems. It will really just depend. But are there any questions on how we're going from radical format into exponential format with these fractional exponents? Okay. So now we're going to go the other direction. We're going to write them in radical form. So they're going to give you exponential form, and then we have to take it into that radical formatting. And sometimes they will be very specific, and they will say, do not simplify. And if they say do not simplify, then you don't simplify. And I'll show you what I mean. Here with 9 raised to the 1/2, remember the top number of our fraction is going to stay with our base. The bottom number becomes our index on our radical. So this would be taking the square root of 9. If it said, do not simplify, you would stop. We would stop there. If it says simplify, or if it doesn't state anything, if it just says write in radical form and then there's no other instructions, then you can go ahead and carry it out if you can do the operation. We can take the square root of 9 and we get 3. But if it stated do not simplify, then we would stop at the square root of 9. So just be aware of that. And remember, from 11.1, while the square root of 9 does give us a positive 3 or a negative 3, we're going to give the positive or the principal square root for all of our answers. All right, let's look at the third root of negative 8. Our index is an odd number, so we can take the radical of a negative number. And again, if you don't know what your cubes are, that's okay. You can use your calculator. It will help you. But 2 times 2 times 2 is 8. So negative 2 times negative 2 times negative 2 would give you the negative 8. So this is negative 2. Your calculator can actually do, I'm pretty sure, all of these. But when it comes to using this information on a test, like a handwritten test in your next math class in college algebra, you definitely want to know how to apply it this way. Let's see. Yep. So if you can see that, that's a little better for the calculator. You can actually type negative 8 raised to the 1/3 power, and it does go ahead and do that for you. So know you can check your work here as you're working through your problems. All right. C says y to the 1/4. Remember, the 1 stays with the y, the 4 becomes our index, so this is the 4th root of y. In Pearson, they give you all kinds of options along that bottom bar whenever you click inside the answer box, so that you're able to actually type in the 4th root, the 8th root, the 22nd root, whatever it is that they give you. D, we have 10x squared y. All of that is raised to the 1/7. Here's the nice thing. We don't have to distribute that before we take the radical format. The fact that that's outside of the parentheses is simply telling us that everything inside the parentheses is going to be our radicand, or going to go under our radical. So the 1 still stays with everything in here, and that 7 pops out to be our index. Nothing else we can do. Last one, what do you think E looks like? It says 5rs to the 1/2.
Square root of 5rs.
Okay.
That comes out to the absolute value of 5rs.
Okay. Anybody have a differing opinion of what this looks like? Okay, you're a little bit closer. Notice where the exponent is versus where the exponent is up here.
Oh.
Yeah.
5r square root of s.
5r square root s. The exponent only applies to the term right in front of it, unless there's parentheses. If there's parentheses, it goes to everything that's inside that parenthesis. But for here, this is saying we have 5r, and then we have s to the 1/2. That 1/2 does not apply to anything besides the s term. And so we have to be careful about that. So yeah, as weird as this kind of looks, it would be 5r square roots of s. That's exactly right. Any questions on any of those, going from the exponent into the radical format, before we make it a little bit more interesting? Okay, here's something that's really important to note. It goes along with this, and it reminds us of stuff we learned back in chapter 5. Note that negative 25 to the 1/2 is not the same thing as parenthesis negative 25 to the 1/2. We talked a lot about how when you have a negative number raised to an exponent, unless you have parentheses around that negative out front, then that negative is not included. We talked about that in chapter 5, and it's true here with our radicals. Because what happens is that 1/2 only applies to the 25. It doesn't apply to that negative. We can factor it out front like it's a negative 1 times 25 to the 1/2. That would be the negative of radical 25, which would give us negative 5. We can actually compute this all the way down. Over here, that negative is inside the parentheses, so we're taking the square root of negative 25, but that's not a real number. We can't do that. So we have to be really careful in what the problem actually presents. And I know for a fact you have one like this on your homework today. Number 11 is very, very similar. And so you have to pay attention to whether or not you have parentheses or not, because it changes the problem entirely. Questions, comments, clarifications on that? All right. Then we're going to start actually simplifying these radical expressions using our fractional exponents. We're going to see how it simplifies our life a little bit. We're going to do 4 of them. We have the square root of x to the 6th. And so we're going to translate this over to fractional exponents, and then we're going to simplify with our fractional exponents. That doesn't always guarantee that you won't end up with a radical answer in the end. Your problems are very specific in instructing you how to do this, where they'll tell you translate into the fractional exponent and then translate back into the radical if you need to. But all 4 of these examples do play pretty nice and simplify completely out. And so we will see that. So this would be x to the 6th raised to the 1/2, because we're taking the square root of everything that's underneath. Then we apply our power rule from back in chapter 5. Power rule states if you have a power raised to a power, you multiply those powers together. So we'd have x to the 6 over 2. Well, 6 divided by 2 is x to the 3rd. And if you took the square root of x to the 6th or anything to the 6th power, you would find that that thing is raised to the 3rd power. It does work out that way. And that's how we're going to approach all of these. Y to the 21st, we're taking the cube root of that. So we'll have y to the 21st raised to the 1/3 power. Multiply those exponents together so that you have 21 over 3. And we get y to the 7th. In my notes, there's a typo. Just so you know, I can't divide 21 by 3 in my handwritten notes. I wrote 9. Don't know why. It was probably a Monday. Any questions on these 2 before we make it one step harder? Although not really. It's not really any harder. It just looks a little different. Because here we had our variables raised to exponents underneath our radicals. Here we have just a regular variable underneath our radical, and then all of that is raised to a power outside. Still works the same way, because here we're going to have w. The 4th root of w is w to the 1/4. But then all of that is raised to the 20th power. Again, we have a power raised to the power. It's just our fractional powers inside our parentheses this time. 1/4 times 20 is 20/4. 20 divided by 4 is w to the 5th. So who wants to be daring And tell me what the last one ends up being. That's exactly right. Good job. Z to the 7th. Inside, we're taking the 5th root of z. That'll be z to the 1/5. And all of that is being raised to the 35th power. 1/5 times 35 will give me 35/5. 35 divided by 5 is 7. So we end up with z to the 7th. Great job. Questions, comments, concerns on how we did any of those? All right, let's do a couple more examples, a little bit different. Told you today was lots of examples. I'll flip that over so we don't have conflicting work. These problems simply state simplify. Some of them are numerical in that they have numbers, so odds are you're going to get a single number answer. Some of them have variables. You will encounter both styles of problems. So this one doesn't give us a lot of guidance in which direction we should go, whether we should leave it in the radical format or we should put it in the fractional format. Should we go back and forth? So I'm going to give you a couple of pointers. Like I said and kind of showed you, though, a lot of times if it's a numerical problem, you can just use your calculator if you so choose. But the process of knowing how to go back and forth is very beneficial because you will not always have just numerical numbers. And especially when you move on to college algebra, you will be encountering these problems that have numbers and variables and everything else that are kind of messy. But for this first one, when I have 4 to the 3/2, remember that the bottom number is the index on our radical. So this is saying we would have 4 to the 3rd underneath, and we'd be taking the square root. What I would choose to do is I would figure out what 4 to the 3rd is. Well, 4 times 4 is 16. 16 times 4 is 64. And then I would ask the question, what's the square root of 64? 8. That's exactly right. There's another way that you can look at these problems where when I have 4 to the 3rd, I'm going to come over here to the side a little bit just so I have room for my other problems. That's saying I have 4 squared times 4 underneath my radical. Well, when you square root a square, it goes away. So the square root of 4 squared is 4. The square root of 4 is 2. So notice I still am going to end up with 8. Different path, same answer. One of them you're splitting up your 4 to the 3rd. The other one you're actually computing what 4 to the 3rd is and then taking the square root. The one nice thing about taking this approach is sometimes you don't have a perfect square or a perfect cube or whatever the case may be in your number aspect. But you are able to take a portion of it and square root it. And that is an important lesson to kind of learn how to play with, is the splitting and square rooting parts of it. I know for a fact that comes up quite a bit in college algebra when it comes to simplifying the quadratic formula because there's a lot of square roots and radicals and stuff like that in that section. All right. For B, we have the 6th root of 49 to the 3rd. So for me, 49 is quite a large number. So I'm going to probably choose to convert this over to my fractional exponents and then play around with it and see what I can come up with. There's no real right or wrong approach. If you want to leave it in radical form and play with it in radical form, you can. I just know I don't want to take 49 to the 3rd because to me, my mind doesn't work with numbers quite that large. And so if I can keep them simple, I'm going to try and do that. So the number that was with my exponent in here is the top number. My index sweeps around to become the denominator. Well, this is the same thing. 3 divided by 6 is 1/2. Okay, so this makes a little bit more sense to me. I can take the square root of 49. I can do that because 49 is 7 times 7. And so sometimes by flipping back and forth between the exponential form and the radical form, it helps to be able to make a problem that would be really, really complicated or seem really complicated a lot easier. Because 49 to the third power is 117,649. I would have no idea what the sixth root of that is. Obviously, I could type it into my calculator, but I can also do a simple process to where I can do the entire problem by hand without a calculator. And the less I rely on this, the better. Questions on the first two, since those are the two numerical examples out of this set. All right. Next, we have the fourth root of xy raised to the 20th power. So I'm going to opt to translate this over into my exponential. It was the fourth root, so that 4 becomes my denominator. 20 divided by 4 is 5. So this will be x to the 5th, y to the 5th. Again, in my notes, I stopped at this point, but you can keep it going one more step to where you distribute that power. The last one is very similar. We have the 15th root of z, all of that raised to the 5th power. So I'm going to do what's inside my parentheses first. 15th root of z will be z to the 1 over 15. And all of that's raised to the 5th power. Power rule says I multiply my powers together. So that'll be z to the 5 over 15, which is z to the 1/3. Now, at this point, I'd need to read my instructions, which I know there's not any for my handwritten problems, but I'd need to see what Pearson wanted. If Pearson wants a fractional exponent, I would stop here. If Pearson wants radicals, then I would need to go ahead and take this one step further so that I would have the third root of z. It just depends on what Pearson's asking for. All the rest of ours worked out to nice numbers or variables. They didn't have any fractional exponents. There was no other radicals. So it would really depend on what's Pearson wanting. Either of these would be correct, just depending on what they're asking for. Questions, comments, concerns? Okay. And here's a little refresher and an additional note. A note that I kind of brought up with our first example here. It says, note that the nth root of a to the n is a to the n over n, which is a. We did that when I showed you that you could split, and you take the square root of 4 squared, and you get 4. That's because you would have the square root, or you'd have 4 raised to the 2 over 2, which is 4 to the first power, which is this. So that's what this note says. It says unless n is even and a is less than 0, then you can figure this out by just taking the absolute value of a. Remember, this absolute value of a business comes from our 11.1 section. So as long as a is positive when we have an even index, we can do this process. Do what? It's absolute value of a. Oh. Yeah, it's very crooked if I have to make it all fit, but sorry. There we go. I can get it to fit that way. So there's a general example right here where I'm taking the 6th root of xy to the 6th power. Notice that whenever I convert this over to my radical or my rational exponential form, that would be 6 over 6. Well, 6 divided by 6 is 1, leaving me with just the xy. So that's just to prove that the nth root of a to the n is a. And then the other information right here is just a reminder from 5.1 and 5.2, because it's been a minute. Those were the first 2 lessons of the entire semester. These are all of your different rules for exponents, and you will need all of these as you use your homework today. As you progress through chapter 11, as you move into college algebra, these are all very important rules that you are going to need to know how to play with. So remember, product rule is when the bases are the same, you can add the exponents together if you're multiplying them. The quotient rule is if the bases are the same and you're dividing, then you can subtract those exponents. The negative exponent states that if you have a base raised to a negative exponent, then you pop that base with that exponent down to the bottom of your fraction and drop the negative. If you have 1 over a to the negative m down here, then it would pop up to a to the m outside of the fraction. So if you have a whole number raised to a negative, it becomes a fraction. If you have a fraction, then it becomes the whole number, or you end up flipping your fraction depending on what the problem looks like. That's one that comes up quite a bit in the homework today. The 0 exponent rule states that anything raised to the 0th power is 1. And then power rule, or raising a power to a power, however you want to think about that rule, you multiply or you distribute that power. So here we multiply the powers together. When you have more than one term inside your parentheses, you're distributing that. You're still multiplying your powers, it's just you have more than one power. You have the power on the A, which is 1. You have the power on the B, which is 1. So you're really distributing that m inside. Same thing here for this fraction. So you definitely want to keep all of those rules in the forefront of your mind. And there's one more that I listed at the top of the next page, but I'm going to go ahead and, it's not really a rule, it's more of something to notice as you're using your exponents and your radical formats. If you're taking the nth root of a to the m, that's no different than taking the nth root of a and all of that raised to the m. It's really what we did just a little bit ago. I'll let you write that down for a second, and then I'll remind you of these couple examples we did. Okay, hopefully you've got that. When we did, I'll flip over, these 4 examples, sometimes we had the exponent underneath here, and then we just applied the index outside. But in this example, we had the 1/4, and then we applied the 20. If we had w to the 20th here underneath the radical, it would work the same way, because we would have w to the 20th raised to the 1/4. Well, we're still multiplying those 2 powers together, which would still end up giving us w to the 5th. So this does work. That little note does work every time. And sometimes it's just easier to think about it in that, like by converting it this way, maybe it's a little bit easier. All right, let's do some examples. Lots of examples. We're going to remember all of our exponential rules. This is 8 to the negative 2/3 power. If you have a negative exponent, always deal with the negative exponent first. Always. So whenever you have a whole number raised to a negative, what that means is on the very next step, you're going to put it in the denominator of a fraction, and your exponent loses the negative. Nothing else changes about that exponent. It just drops the negative. Now I would apply the 2/3 to the 8. Remember, the 2 stays with the 8. The 3 becomes the index on our radical. Cube root of 64 would be 4. So the answer is 1/4. One thing to note, you will never leave a radical in the denominator of your fractions. So if you end up with something that's 1 over the 3rd root of 64, you know you're not done because you have a radical in the denominator. There's going to be something else that simplifies, or your problem will tell you to write it in rational equation, like rational exponents. Because you don't ever want to leave this written this way. And really, you don't ever want to leave rational exponents in the denominator either. And we will see that there's ways for us to eliminate those as well. So get rid of your negative, and then apply whatever your powers are, and simplify from there. Questions? All right. Let's look at B, which is negative 27 to the negative 5/3. Again, we want to deal with that negative exponent first, so that means I'm going to put everything down in the denominator of a fraction. And I'm going to drop the negative on the 5/3. I don't get to drop the negative on the 27. That doesn't magically become positive just because I moved it to the denominator. Now I'm going to apply my 5/3 power. That means I have the 3rd root of negative 27 to the 5th. Now, this is one of those times where I'm going to use that special rule that I indicated, and here I can show you up top. I can put it up there. Because for me, I could type negative 27 to the 5th into my calculator, and I'm going to get a really big gross number that I don't want to deal with. What is that? 14,348,907 negative. I don't know what the cube root of that is. And yes, my calculator can figure that out, but if I have a method that's going to allow me to figure this stuff out without a calculator, I'm going to do that. And so what I'm going to do is I'm going to use this little rule where the nth root of a to the m is the same thing as nth root of a raised to the n power. So instead of thinking this as the 3rd root of negative 27 to the 5th, I'm going to think of it as the 3rd root of negative 27 raised to the 5th. Because I know what the 3rd root of negative 27 is. Because negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. All of this in here is negative 3. Now, whether or not I know what negative 3 to the 5th is off the top of my head, maybe not. But that's a much nicer number to figure out or to play with in my calculator than 14 million. Negative 3 to the 5th power is negative 243. So there's multiple different ways you can work these problems. Like I said, you could have taken this to the 5th and then taken the cube root. You'd still get the exact same answer. Or maybe at this point, or even at that point, you're like, I'm just going to use my calculator. You can. But when you walk in on a test day and you forgot your calculator and you don't know how to get from here to here without one, that's where you're kind of biting yourself in the butt. So learn the process. Use the calculators to help you check your work. That's what I recommend. All right, I'm going to skip a couple of these because they're very similar, like my handwritten ones. Notice in my handwritten notes, I have a lot of examples. I'm going to skip to one where they want us to leave it with exponential form. So they want us to leave exponents in here. They don't want us to go to radical. We can't completely simplify it out. I'm going to do F in my handwritten notes. This is a to the 1/2 times a to the negative 2/3. This problem specifically, you have multiple different ways you can approach it. You can approach it by moving that negative exponent and making it a positive exponent first, or you can use your product rule where the bases are the same, you're multiplying them together, so you would add the exponents. This would be a to the 1/2 plus negative 2/3, which is the same thing as a to the 1/2 minus 2/3. You do have to play with fractions, so you do have to get common denominators. Whoops. Common denominator would be 6, so that would be 3/6 minus 4/6. I cannot write today. 3/6 minus 4/6 would be a to the negative 1/6. We can't leave it, even if it tells you to leave your problem in exponential form, it will tell you to leave it with positive exponents. This does not have a positive exponent, so we would need to take it one step further to have a positive exponent. If you did not do it this way and you got rid of that negative exponent first, honestly, you would end up probably doing the exact same steps, because then you would apply the quotient rule, which is where you subtract, which is where you get the exact same answer. But your problems will tell you if they want you to leave them in fractional form, but they will specify that they want positive fractions. So this would not cut it. Let's do one more. We're going to do h, because h has a little bit of everything going on. We have 9x to the negative 4, z to the 2/5, all over z to the negative 3/5, all of that raised to the 1/8. So lots and lots and lots of stuff going on.
That's a 9 or a G?
That's a 9. It just kind of blotted there at the end. Here's what I don't recommend doing. I don't recommend bringing this power into the mix of things until after you've done everything in here that you possibly can. So first thing I notice is that I have a z on top, I have z to the 2/5, and I have the z to the minus 3/5 down here. Well, that means I can bring that z to the top because it's a minus down here, so I can bring it up. I can do the same thing with my x's. I can take x to the negative 4th, and I can pop it down below to where they're kind of switching places. Z to the 2/5, z to the 3/5. Now I can do my product rule, and it's actually really nice because they already have the same denominators. So when I go to add these together using my product rule, I'm taking z to the 2/5 plus 3/5. What's 2/5 plus 3/5? 5/5, yeah. 5 over 5 is what? 1. So I'm just left with a nice little z. And my x to the 4th is just down there too. Notice everything that had a fraction or a negative became a nice thing. If I were to have applied that 1/8 first, everything would have had bases of 8 or bases of 40. It would not change your answer in the least. It's just you're dealing with more complicated numbers, and everything has a fractional exponent, and it becomes kind of a mess. If you can hold off that until the end, that's better. So now at this point, I would make sure this 1/8 exponent gets brought into everything. The whole number included. Any number gets that power as well, so don't forget that. So I have 9 to the 1/8, z to the 1/8. And then down here, I would have x to the 4/8, but 4 over 8 simplifies to what? 1/2. So when they want you to leave your answers in fractional form, they will ask you for positive fractional exponents, And they will have you simplify those fractional exponents. You don't want to leave it as 4 over 8 in this exponent. You'll want to take it down to 1/2.